So now I want to go through how to graph a polynomial like this one here. So -1 times x plus 2 times x minus 1 squared. So the way we could start out this process is to first figure out the end behavior of the graph. Now, end behavior is determined by end behavior. End behavior is determined by the leading coefficient of the polynomial. So it's nice that this thing's in factored form. The one thing that gets a little trickier when it's in the factored form is identifying the leading coefficient. It's not too bad here though. Okay, so the leading coefficient in this case is -1. So imagine you multiply this whole thing out. You would have negative times some power of x. The important thing about the the leading coefficient is the fact that it's negative. That's what we really want to note about the leading coefficient. Also, the degree. And the degree is something also that's a little trickier to find when it's in the factored form. Imagine you multiply this thing out. So you don't have to actually multiply it out to find the degree. But just imagine you multiply it out, because we don't need to find every single term, just the highest power. So what would the highest power of x be? Well, if I expand out x minus 1 squared, I'll have x squared minus 2x plus 1, but we don't care so much about that. We'll have x squared in front, times another x here, so that'll give us x cubed, times the -1. So the leading term is negative x squared. Oops, cubed, sorry. I already noted the leading coefficient is -1, that's the negative here. The degree is 3. And what we need to note about the degree is that it's odd. So if you have a negative leading coefficient with an odd overall degree, then what you use as your model is the graph of y equals x cubed, which looks like this, but with a negative leading coefficient it's going to flip, so it's going to be up on the left and down on the right. That's the end behavior. So it's like x cubed, which is an increasing graph, except if you multiply by -1 in front, that's going to reflect it. So now it's a decreasing graph, up on the left, down on the right. Okay, so first thing is determine end behavior, which is determined by the leading coefficients, the number in front, and the degree overall. Okay, so I'm going to get rid of this information. We've got the end behavior. The other thing we want to note are the zeros and their multiplicity. So the zeros of this polynomial are -2, because if you set x plus 2 equal to 0, you'll have x equals -2, and 1. If you set this x minus 1 squared equal to 0, you'll get x equals 1. -2 has multiplicity 1, because we just have x plus 2 to the first. So this has multiplicity 1. 1 has multiplicity 2, because another way to write this out would be -1 times x plus 2 times x minus 1 times x minus 1. So you can think of multiplicity as how many times is this particular value a zero of the polynomial. So x equals 1 would be a 0 twice. That's the way I think about it. So multiplicity is how many times do you get that as an answer. When a 0 has odd multiplicity, like this one here, the graph is going to go through the x-axis. And when a 0 has even multiplicity, like this one here, then the graph will touch the x-axis and turn around. Okay, so now we're ready to graph this thing. I will say one other thing you might find when you're going to sketch the graph of a polynomial is the y-intercept. And this one's kind of optional in my mind. The zeros, remember, are the x-intercepts. If we want to also find the y-intercept, you would do that by plugging 0 into this function. So f of 0 would be -1 times 0 plus 2 to the first times 0 minus 1 squared. So that would be -1 times 2, so -2 times -1 squared is just 1. So the y-intercept is -2. So the y-intercept, thinking about how much I want to space this, I guess I'll space it a little bigger. Y-intercept is -2. X-intercepts are -2 and +1. And now we can draw the graph. So find the end behavior, find the zeros and their multiplicities, and then you're ready to sketch the graph. So when we're actually sketching, first plot the intercepts. So again, the zeros are the x-intercepts. To find the y-intercept, you substitute 0 for x. Then use the end behavior to draw the ends of the graph. I'll put to draw the ends. So end behavior is up on the left, like this, down on the right. So that's what I mean by draw the ends of the graph. And then use multiplicity of the zeros to fill in the middle. So at -2, that had odd multiplicity, so the graph goes through the x-axis. And we know it's got to come down and touch this y-intercept at -2. Now, without calculus, I don't really know that it turns around at -2, maybe it doesn't, but that's something that you're not responsible for in pre-calculus. You have to have it go through the intercepts. You don't have to figure out exactly where does this graph turn around, but at some point it's going to turn around and come back up and touch that next intercept. You know that much. So if you want, you could have your graph dipping down further and then coming up, or just turning around right at the -2. I guess maybe I'll draw it like that, just for the fun of it. Now that looks weird, doesn't it? I don't like how that looks. Here, I'm going to have it turn here. But like I said, you're not responsible for getting that part of the graph right. We're just looking for a good general sketch of the graph. Okay, now at 1, I mean, we've basically got the graph filled in at this point, but at 1, we know it's even multiplicity, so we were expecting the graph to touch and turn around, which is what was going to happen anyway, because we were going to come up, touch the next intercept, and then we already knew because of the end behavior that the graph should go back down from there. So here's a decent sketch of that function there, -x plus 2 times x minus 1 squared. I'd like to repeat this process one more time with one other function. So I'm going to get rid of all of this. Luckily this is a video, so you can rewind if you're mad at me for erasing. And then I had one planned out, so it's the one that I have put into the notes online for this section. So it's 3x to the 4th minus 6x cubed. This time I'm not presenting it in the factored form, plus 3x squared. Same deal, we want to graph the polynomial. Well, you're definitely going to want the factored form for that polynomial. I mean, it's nice to have the expanded form as well, but we're going to want the factored form. One nice thing that we notice here, there's a common factor of 3x squared. So we can factor out 3x squared. If we do that, the remaining factor would be x squared -2x plus 1. So then that, if we want two numbers whose product is +1, the sum is -2, that would be x minus 1 times x minus 1. So x minus 1 squared. Okay, so there's the factored form of that f of x. Now when we're drawing the graph, we want to note the end behavior, the zeros and their multiplicities. So end behavior. Well, if the leading term here is 3x to the 4th, then we know that the leading coefficient is +3. And we know that the degree is 4, which is even. So even degree in behavior is going to look like a parabola, either pointing up with a positive leading coefficient or pointing down with a negative leading coefficient. So this one's got a positive leading coefficient, even degree. In behavior is going to be that it points up. It's going to look like a parabola pointing up. I leave a space in the middle though, because the higher the degree, the more twists and turns there might be in the middle. Most likely it's not going to look like a straight parabola. There's going to be some turning points in between the two ends of the graph. Okay, now the zeros. The zeros of this polynomial are x equals 0, which students often overlook that, but you need to set this factor equal to 0, and you get x equals 0 with multiplicity 2, because of the degree 2 there. and x equals 1 with multiplicity 2. So this time they both have even multiplicity 2. This time they both have even multiplicity. Okay. Oh, and the one other thing I found before, and I guess I'll do it again, is the y-intercept. So we plug in 0. Oh, and then wait a second. If I plug in 0, I'm going to get 0. We already know that 0 is a x-intercept here. Okay. So when you're drawing the graph, first plot the intercepts. That was in my list of 3 things over here a minute ago. First thing was plot the intercepts. So intercepts are at 0 and 1. I'm going to space this out. Now draw the end behavior. So end behavior, if you zoom way out on this graph, it looks like a parabola opening upward. Now use the multiplicities to fill in the middle. So 0 has multiplicity 2. That means the graph touches the x-axis and turns around. And then at some point comes down and touches this next x-intercept at 1. Again, even multiplicity, so it touches the x-axis and turns around. So this is our overall sketch of this polynomial. So just reiterating, you plot intercepts, and then use end behavior to graph the 2 ends of the graph, and then use multiplicity to fill in the middle. That's your overall strategy for graphing polynomial functions.